Alright everyone, so we have watched 10.2, maybe we started the homework a little bit. Now 10.3 is very similar, it's just instead of an arithmetic sequence and series where the pattern is to add or subtract a constant, now we have a geometric sequence, which now instead of the pattern being addition subtraction, the pattern is now to multiply or divide. So our success criteria, I can successfully find the common ratio for a geometric sequence. I am able to write terms of a geometric sequence. You can find them with the pattern. I can confidently use the formula for the general term of a geometric sequence. And I am able to use the formula for the sum of the first n terms for a geometric sequence. So that's the series. Okay, so we're basically doing the same thing we did with arithmetic. It's just now it's geometric. The pattern is to multiply or divide. So, geometric sequence is a sequence in which each term after the first is obtained by multiplying the preceding term by a fixed non-zero constant. Okay, it's not going to be 0 because then everything would be 0, right? Now, instead of a common difference, what we're going to have is a common ratio. That's the R. Okay, now you can find the common ratio by taking a term and dividing it by its previous term. Okay, remember dividing is the same as multiplying by the reciprocal. We're just going to write everything as multiplication. Now, this little picture here, this kind of is a perfect example of a geometric sequence. Okay, looking at how many squares you have. Right here we just have 1. Then we go to 5. Then we have 25 and so on and so forth, right? And then we're going to have 125 and then 625. So basically the pattern is 2 times 5 times 5 times 5. Now, here, which basically is this one here, okay? Now for this one to go to 4 to 8, we can either add 4 times 2, but we want a constant pattern, okay? If I do 8 plus 4, I'm not going to get 16, so it's 8 times 2, and 16 times 2, 32 times 2, stuff like that, and that's your pattern, okay? So the common ratio. Sometimes your common ratio can be negative, okay? If you go positive to negative to positive to negative, your common ratio is going to be a negative, okay? And if you're going down, okay, really to divide by 3 is the same as multiplying by a third. So just something to keep in mind with that, all right? Now, because the pattern is to constantly multiply or divide, this is actually going to be, so geometric sequence is going to be exponential. Now remember with exponential, it was the y equals a times b to the x power, right? When your x is the exponent, that is exponential. With arithmetic, it was linear, right? We keep adding or subtracting, and that's our pattern or our slope, right? So basically what we're going to do is, if I want to find some terms, right? So let's say I want to write the first 6 terms of a geometric sequence where the first term is 6 and the common ratio is a third. So my first term is 6. They gave it to me. My second term is going to be my first times a third. So 6 times a third, I get 6 over 3 or 2. The third term is the second times a third. So 2 times a third, or 2 divided by 3, 2/3. A of 4, we have the third term times a third. So it's 2/3 times a third, which means it's going to be 2 over 9. The fifth will be the fourth times a third. So 2/9 times a third is 2 over 27. And then the last term, we will have 2 over 27 times 1/3, so 2 over 81. So here is our geometric sequence, okay? It's times a third, times a third, times a third, times a third. Go on to checkpoint 1, all right, and try it on your own. Okay, So, first 6 terms of a geometric sequence with the first term as 12 and the second term you find by taking your common ratio of 1/2. So 12 times 1/2 is 6. 6 times 1/2 is 3. Our fourth term is 3 times 1/2, which is 3/2. Leave it as a simplified fraction. You know MyMathLab's going to ask you for that. A of 5 is going to be 3/2 times 1/2, so it's 3/4. And then our sixth term is 3/4 times 1/2, which is 3/8. Alright? Now, we had a general term for arithmetic sequences, so we have a general term for geometric. Now remember, geometric means exponential, so it's the same here. Okay? It's a lot like our y equals a times b to the x. Alright? If we want a term, we're going to multiply that common ratio n minus 1 times, right? To get from the second to the fifth term, you have to multiply that r 3 times, right? 5 minus 2. Your first term is going to be like that y-intercept in a way, okay? That's starting amount. And then your r is your rate of change, okay? So, find the 8th term of the geometric sequence, whose first term is negative 4, and whose common ratio is negative 2. So real quick, let's just make the nth term. Our nth term is going to be the first times r to the n minus 1, right? So the nth is going to be negative 4 times negative 2, make sure it's in parentheses, to the n minus 1. So this is the nth term for this pattern. So my 8th term is going to be negative 4 times negative 2 to the 8 minus 1 power. So follow my PEMDAS, it's negative 2 to the 7th, which remember with this, when you do this in your calculator, make sure you're writing in parentheses negative 2 and then to the 7th. It is, if you put negative 2 to the 7th without parentheses, it will not take that negative into consideration when raising it to the power. Okay? Another thing to keep in mind, if it's an odd power of a negative, you're going to get a negative answer. If it's an even power of a negative, you're going to get a positive answer. Just something kind of to keep in mind. Negative 2 to the 7th is negative 128. So negative 4 times negative 128 is positive 512. So the 8th term is 512. Okay. Pause the video. Try out checkpoint 2. And let's see how we do. Alright. So, find the 7th term of the geometric sequence whose first term is 5 and whose common ratio is negative 3. So let's find the nth term first. So my first term is 5. My common ratio is negative 3 to the n minus 1. So now that we want the 7th term, it's 5 times negative 3 to the 7 minus 1 power. So negative 3 to the 6th is going to give me 729. Positive 729 because it's an even power. So I'm going to get 3,645. So A of 7 is 3,645. Now something to keep in mind, because it is geometric and we are multiplying or dividing, it's going to start growing or decaying at a much faster rate. The numbers are going to start getting much larger than they would have with arithmetic. Okay? Alright. So I want to give you a problem like this because how would you kind of figure out what the common ratio it is if I gave you information like this? Alright, you will have a problem like this on your homework assignment for 10.3, so just something to keep in mind. So the table shows the population of the United States in 2000 and 2010 with estimates given by the Census Bureau for 2001 to 2009. Okay, so these are actual numbers and the rest were estimates based on the growth. All right. Now, A says show that the population is increasing geometrically. Well, if it was geometrically, then I would be able to find any term by taking the first term and timesing it by r to the n minus 1, right? That's the general term. Or I would be able to take any number and find it and take the previous one and times it by my common ratio, right? Well, I need to see, the only way that's going to work is if, to get from problem to problem, like I'm showing here, I would have to constantly multiply by the same number. So what I'm going to do is I'm going to try and make sure that I'm going to get that. So my ratio, my common ratio, would be so this is my first term, right? A of 2, A of 3, A of 4, and so on and so forth, right? So I know my ratio, just like I said before, right? Your ratio is going to be your term divided by the previous one. You always have to put the one that comes next above the one that came before. So I would have to do A of 2 divided by A of 1. So 284 divided by 281.4. Now with this, try and give me about like 3 decimals or so just to kind of see if the pattern is. Now it's not going to be absolutely perfect because nothing's absolutely perfect like that with a real life model, but we want to see if it's close enough. So if you multiply this, or divide this, you will get about 1.009, and it keeps going, but if you round like 3 decimals or so, I usually go 3 to 4 just to kind of be more accurate. Now, if this is true, then if I keep going and going and going, I'm going to get the same thing, right? So technically, if it's a common ratio, then this would also be the same when I do A of 3 divided by A of 2. Or if I did the fourth term divided by the third, or the fifth term divided by, and so on and so forth, right? So I'm just going to do at least the first 3 to show you. So my third term was 286.6 divided by 284. My fourth term is going to be 289.3 divided by my third, which is 286.6. Now, if you do these in your calculator, you'll see you get about, I've rounded 3 decimals, all of them give you 1.009. So since the common ratio, or since the ratio is constant from term to term, it is increasing geometrically. Okay? Now kind of think about this as like, remember with exponential we did our compound interest, right? So think about this as like that 1 is like 100% of what you already have. So it's growing exponentially by about 100.9%. So about 0.9% of a growth every year, it's estimating. You don't really need to know that. It's just something to kind of be able to tie it to what we've already learned. So that proves it's growing geometrically. Now for B and C, it's what we've done before, just we did it arithmetically, right? So for B, write the general term of the geometric sequence. So I want the n term of the geometric sequence, modeling the population of the U.S. in millions n years after 1999. So that means the year 2000, that first one, is our first term. So 281.4 times, now my common ratio I found to be about 1.009 to the n minus 1 power, right? So there's my general term. It's the first times your ratio to the n minus 1 power. So C, to project the U.S. population millions by the year 2020. I want to use that formula to figure it out. Now the year 2020, I got to see what's the difference between that and 1999. And I'm going to have 21. So I'm going to find the 21st term here. So 281.4 times 1.009 to the 21 minus 1 power, or the 20th power. You could put this in your calculator, just make sure you have parentheses in the proper spaces, and you are raising the 1.009 to the 20th power before you multiply 281.4. So I'm going to get, for A of 21, I'm going to get about 336.6 million people. Okay, because remember that number that you get is technically in millions. Now the reason I chose to round to the nearest tenth, if you look at your table, everything else is rounded to the tenth, so it kind of helps you to figure out how you should be rounding those terms. Most of the time on MyMathLab, it'll tell you how to round. If you see everything in tenths, though, just stick to tens. Okay, so what I'd like you to do right now it's not a word problem, but still something you could do. I want you to write the general term for this geometric sequence by being given what I gave you here, and then use the formula to find the 8th term. So I want A of n, and I want A of 8. A of 8. Okay, pause the video, try it out. Alright, so the nth term, remember, will always be the first term times your common ratio to the n minus 1 power. Well, my first term is 3, and I got to see what my common ratio is based on the pattern, okay? So 3 to get 6, I got to times 2. To get 6 to 12, I times 2. Times 2, I'll get 24. Times 2, I'll get 48, and so on and so forth. You could also use that whole idea of the second term divided by the first. So 6 divided by 3, you get 2. So that's your common ratio. So 3 times 2 to the n minus 1. There is your nth term. Okay? You don't have to worry about simplifying like we did with arithmetic, because you can't really simplify this exponential part. So now that I have an nth term, I can now find any term I want. Alright, you don't have to sit there. I know we have the first 5 terms, and then 48 times 2 would give me the 6th, then times 2 is the 7th, then times 2 is the 8th. But what if instead of finding the 8th, I asked you to find the 80th? You're not going to want to sit there and keep timesing 2, timesing 2, timesing 2. So you're going to want to use the formula instead. So the 8 of the 8th is going to be 3 times 2 to the 8 minus 1 power. So it is going to be 2 to the 7th, which we already did before, but we did negative 2, right? So 2 to the 7th is 128, and then times 3, I'm going to get 384. So I have my nth term and my 8th term. Alright, so that's how we deal with the sequence, finding the pattern to help us jump ahead and find the next term, right? Well, what if I asked you to find the sum of the first 10 terms in your series and stuff like that? There is a formula just like arithmetic, alright? And it's this, okay? Remember, the S for series, and whenever you see series, it's going to be sum of this many terms. Now, all you're going to need for this, you need your n, how many terms you have, you need your first term, and you need your common ratio, alright? It's definitely, it looks a little more complex, but again, follow PEMDAS, take your time, it will work out, alright? And because the numbers are growing faster, you're going to get larger answers, okay? So the more time you take, you'll be fine. So, example 4, find the sum of the first 18 terms. Sum is the key word of the geometric sequence. So, since it's geometric and I want the sum, so my n is 18. I'm going to use S of 18. I'm going to use this formula, right? My first term is 2. And my pattern, if I look to get to negative 8 and then negative 8 to 32, I got to times by negative 4. times my negative 4. So that's my common ratio. So I'm going to take my first term, times it by 1 minus my r to the n power, or n is 18th, right? Divided by 1 minus r. Well, my first term is 2. 1 minus my common ratio is negative 4. Keep it in parentheses because you're going to have to raise the r to the power before you subtract. 1 minus negative 4. So the minus negative is plus now, remember? So now I just got to take my time. Now, you can plug all this into your calculator. I suggest what I'd like you to do is at least do this in your calculator so that I could see what kind of answer you're getting. Okay, if you do negative 4 to the 18th, and then you subtract that from 1, so 1 minus whatever you get for negative 4 to the 18th, you are going to get, it's a big number, negative 6, 8, 7, 1, 9, 4, 7, 6, 7, 3, 5. I know, it's going to get bigger because patterns times 4, so the numbers are getting bigger and bigger. Let me make sure I wrote it right. 6, 8, 7, 1, 9, 4, 7, 6, 7, 3, 5. And then all divided by 1 plus 4, which is 5. Now, you times by 2, then divide by 5, and what you should get is negative 2, 7, 4, 8, 7, 7, 9, 0, 6, 9, 4. So, all those numbers added up, the first 18 in this pattern are going to add up to negative 27,487,790,694. They're going to be big like this. Don't be scared. Remember, geometric, the pattern is to multiply, so the numbers are going to get bigger and bigger, and when you add bigger and bigger numbers, your answer is going to get larger. Now, I want you to try checkpoint 4. You're going to get a smaller answer, right? Okay, I hope you paused the video. If not, pause now, try it. If you did, let's get started. So, I want to find the sum of the first 9 terms in the geometric sequence. So, n is 9, my first term is 2. My common ratio, if I look, the pattern is going to be 2 times negative 3. So, S of 9 equals my first term, which is 2, times 1 minus negative 3, my r, to the nth power, so to the 9th, divided by 1 minus my r, negative 3. Minus negative is plus. Now when I do this, I'm going to get, for negative 3 to the 9th, and then 1 minus that, I'm going to get 19,684. 19,684. You're going to times 2, then divide it by 1 plus 3, which is 4. And what you will get is 9,842. So I hope you got that for the sum of the first 9 terms in this geometric sequence. All right. Now, remember when we had summations, right? Remember that arithmetic was linear, right? And geometric is exponential. So, a little similar, all right? So if you see your pattern is a exponential, y equals a times b to the x, right? Your b is really the way the pattern goes is it's 6 times your r to the some power, all right? Or whatever that, it's a. So, I see this as exponential. So, I can, instead of just finding these 10 terms and adding them all up, I instead can do the series formula for the geometric. So they're from 1 to 10, that's 10 numbers right there. So I need my first term. So my first term is 6 times 2 to the first power, because my lower limit is 1. And I'm going to get 2 to the first is 2, times 6 is 12. So here's 12 times 1 minus. Now my r is going to be that rate of change, okay? So in this case, it's the 2 to the nth power, so 10 power, divided by 1 minus my r, which is 2. So s of 10, I'm going to get 12 times. Now 1 minus 2 to the 10th, I should get negative 1,023. And then 1 minus 2 is negative 1. So then when I do all this, I times 12 and I divide by a negative. What I'm going to get for s of 10 is 12,276. So that should be the answer to this, where the I is 1, 10, 6 times 2 to the I. All right? Remember, once it's exponential, think of it as geometric. Why sit there and find 10 terms? All right. Checkpoint 5, pause the video, try it on your own. Okay. So, in this case, I see that this is exponential because the variable is the exponent. So, I can use the geometric series formula. So 1 to 8, that's 8 numbers, so the sum of the first 8 terms is my first term, which my first term is going to be 2 times 3 to the 1, because my 1's my lower limit. 3 to the first is 3, times 2 is 6. So it's 6 times 1 minus my common ratio, that rate of change is the thing to the exponent, so 3 to the 8th power over 1 minus 3. So when I do this, I will get negative 6,560 in my parentheses. So I times by 6 and divide by negative 2. And I get the sum of these 8 terms to be 19,680. Okay. Remember, if you have any questions about any of this stuff, take a picture of what you're confused about, send it my way. All these notes are going to be in your OneNote, so you can look at all the writing I have there as well. Do not hesitate to reach out to me. I know this is a new way of learning, but I'm here if you need any help. Now, the last problem I want to do is just kind of to help you figure out how we can apply this, all right? There is a word problem like this in your homework. I just wanted to kind of help you out with. So, a union contract specifies that each worker will receive a 5% pay increase each year over the next 30 years. One worker is paid $20,000 the first year. What is the person's total lifetime salary over a 30-year period? So, they want to know how much money this person is going to get for their entire life for over the 30 years. So we want to know the sum of the salaries for each year for the 30 years. Now, because it is a percent increase, all right, or if it was a percent increase or even decrease, but you wouldn't want to work for a job that has a percent decrease in your pay, then it's going to be exponential. So we're going to go with geometric in this case. Now, our first year working, we're getting $20,000. And then think about your common ratio. If we're getting a 5% increase, think about what we did for our compound interest and all that stuff. A 5% increase meant 1.05, right? Because it was our original 100 plus the extra 5% we now get. So our rate is going to be 1.05. If it was a decrease, then it would have been, instead of 1.05, it would have been 0.95 because we went down 5% from 100 to 95%. So we have our first term, our rate, and we know we're looking at this over 30 years. So that's our n. And that's all we need to do the sum for 30 years. So we're going to take our first term, 20,000, and times 1 minus our rate 1.05 to the 30th power, all over 1 minus 1.05. Now, if you're going to do this all in your calculator in one shot, please make sure you have parentheses where needed. And if you have that capability to make a fraction, make a fraction. If not, you make sure you do all of this up top first, and then press enter. Then divide it by 1 minus 1.05, which is negative 0.05. Now, when you do this, you will get, so the sum for 30 is, sorry, $1,328,776.95. Now, the reason I rounded that way, we are talking about money. Every penny counts, all right? It's not like a job will sit there and see, oh, 95 cents, let's round it up to $1. They're not going to do that, all right? You get to the nearest cent. So, basically, if the person starts there and works all 30 years, and they start with $20,000, by the end of 30 years, they would have made a little over $1.3 million. Now, looks like a lot of money, but you got to remember, that is how much money you have to use to spend on yourself for the next 30 years to live. So, just something to keep in mind. That's how we can kind of apply this. Now, if I asked you for how much the person's salary will be at the 30 years, then I'm going to ask you for A of 30, the 30th term. But because I asked for the lifetime salary over 30 years, I want the sum series. All right. That was everything from this. Now, the 10.3 homework, you're going to have a few problems, a little bit of everything from this. I did throw like 2 or 3 problems in there where you have to figure out, based on the formula, if it would be arithmetic, geometric, or neither. Remember, arithmetic is when we have the pattern is linear. If it's geometric, it is exponential, meaning the variable is the exponent. If we see something like x squared minus 5, that's quadratic. That's not geometric. That is not arithmetic. It's neither. Okay? So just something to keep in mind. Have a wonderful day, and I hope to hear from you guys soon. All right? Any homework help, let me know. Bye.